With over 50 years of experience in the water and wastewater industries globally, Fluid Components International has developed unique solutions for measurement of liquids and gases. In this next session, we will examine air-gas flow measurement challenges that are commonly found in applications related to processes such as blower systems, aerobic digestion, anaerobic digestion, odor control, cogeneration, CHP, and natural gas submetering. Addressing these application issues on the front end can lead to successful startup of your project. Here to tell us more is none other than the very knowledgeable and talented Adam Schlehan. So Adam, I'm going to give the floor to you. Take us away.
Thanks, Travis, and good morning, everybody. As Travis said, I'm Adam Schlehan. I am the Director of Sales here at Fluid Components International. And yes, we have worked with engineers and contractors and end users in water and wastewater for over 50 years. Digesters, aeration basins, blowers, all types of different applications. And there's two challenges that we routinely hear from our customers that we help them with. The first is accuracy loss in gas flow measurement due to inadequate straight run in a pipe. And the second would be pressure loss. So it could be typically associated with flow conditioning that they would use to help with accuracy loss, but also with other instruments that would cause energy loss and pressure drop. Now, this first topic here, inadequate straight run, our recommendation and what you'll typically hear in industry is that if you have an instrument in the process, the recommendation is that you have 20 diameters of pipe straight run upstream with 10 diameters of pipe run downstream, just so you can have a well-developed flow profile and to get an accurate measurement. That's not always what happens in the real world. We routinely hear questions like, I've got an elbow 3 diameters upstream, or I have a valve. What's that going to do to my accuracy? How's that going to affect my measurement? In this presentation here, we've used CFD models as well as our application evaluation software to walk through some common scenarios and what flow conditioning does for that. So one of the foundational things I'd like to get across here is that the accuracy ratings that you read about in product literature, in the data sheets, on the websites, and the marketing materials, in this case on the screen, we have a white paper. Those are all based on ideal lab conditions, meaning that you have clean, dry gas, plenty of straight run. It's in a lab, which could be very different than the real world nitty-gritty applications that we see in the field. In our case, with thermal mass flow measurement, our published literature, based again on the perfect lab conditions, we get down to about 1% or 0.75% that we publish in our literature. And because we do actual calibration in the actual gas and the media that the instrument is used in, we've routinely actually gotten down to 0.5% of reading or better. But once again, this is the ideal world of a flow lab, which does not always match up to the real world. Now, looking at a flow lab here, what you see, there's got to be several conditions that are present. So number one, you see plenty of straight run with that pipe, that 20 diameters upstream and 10 diameters downstream, no problem. In the lab, we can calibrate with clean, dry gases. And you have reference meters that are also substantially more accurate than the instruments being calibrated. One of the other things here is the turn down range, or that measurement of flows that you're measuring. The equipment in any good lab will measure that full turn down range. And this curve fit graph on the right, again, that demonstrates that in the lab, we are pretty darn accurate. And with these ideal conditions, it's easier to achieve that accuracy. Now, one of the central concepts and one of the primary reasons that having the straight run and these ideal conditions is so important is you want to measure a fully developed flow profile at a point of maximum velocity. So what that basically means is we have this image here, and you have the parabola. The laminar flow is the more bullet-legged end of that. And you want to make your measurement right at that point of maximum velocity, which is right at the top of that parabola, right in the center of the pipe, whether it's laminar flow or turbulent flow, you want your sensing element to be right in the center there to get your accurate measurement. So with the CFD, one more slide here on what the ideal world looks like. This is computational fluid dynamics. And if you look at any of these images, the red represents the gas flow flowing at the highest velocity. The blue, typically closer to the wall of the pipe, is the slower velocity. And we basically set it up from several angles here. This image here with our sensing element in the top right corner, to me, it looks a little bit like a bullseye. And the guideline that I'd have here is you want your sensing element right in the center of that bullseye. So this is what the ideal world looks like in CFD. What we see in the real world on site, elbows, valves, limited straight run. Oftentimes when these projects happen, there's a big focus on the bigger, higher dollar capital equipment, and metering can sometimes be an afterthought, which is why we get the calls on, I have a valve, I have a reducer, I have an elbow, I have this obstruction or that obstruction. What's going to happen to my accuracy? So we do have a few scenarios I could walk through here to demonstrate how that would affect a measurement. So with the measurements that we have, I do have a few diagrams here. On the left, you have a valve. On the far right, you have an out-of-plane elbow. And a little bit different than the CFD, but it does show that when you have these obstructions, that the flow profile is distorted. What you see on the left here with this valve is that the point of maximum velocity, that tip of the parabola there, is not hitting the sensing element right at that point of maximum velocity. The velocities are faster, closer to the wall of the pipe. And you also see similar disruptions to the flow in that far right image with that out-of-plane elbow. So we do have some specifics as to what that does. So going back to CFD, a very common scenario here, we have a 90-degree in-plane elbow, 4 diameters upstream of our instrument. And what you see there is that has an added inaccuracy of 4.3%. Now, if you took that elbow and you installed the elbow, or you installed the meter with an elbow 2 diameters downstream, it wouldn't be quite as bad. It'd still be about 1.2% additional inaccuracy. But the point here being that an elbow upstream or an elbow even downstream, both can have an adverse impact on the accuracy of your measurement. Now, taking a more common scenario that we see with valves, in this case, we have a butterfly valve that's 50% open and it's 5 diameters upstream. And looking at the CFD here, it really throws off the flow profile. You see the ideal, again, that bullseye with the sensing element right in the center of that bullseye, and the actual measurement being made is not at that ideal point. So a butterfly valve 5 diameters upstream will introduce 15% additional inaccuracy. That same butterfly valve 3 diameters downstream, again, you see this trend of downstream versus upstream. It will still introduce an inaccuracy, but in this case, it will only introduce a 1.7% inaccuracy. So here's another common scenario. Usually it's not just one elbow or one valve. Usually it's a multitude of different obstructions that we see when we go on site. In this case, there's a convergence 7 diameters upstream, a butterfly valve, again, half open 4 diameters upstream, and an elbow in plane 2 diameters downstream. You see, this has a pretty significant impact on the accuracy of the measurement that you're going to make. So if you have accuracy requirements of 1% or 2% or 3%, you're getting thrown way off because the impact here can be as high as 18%. Now we'll come back to this example here in a few slides, and we'll talk through what flow conditioning would do in a scenario such as this one. But I do want to go through just some simpler examples to illustrate how flow conditioning works, given different obstructions. So here is a different example. This is a very common blower application that we would see in the field here. There's an elbow, 90 degrees, 9 diameters upstream with a butterfly valve, 7 diameters upstream. And again, this is obstructing the flow. It's not giving us that fully developed profile point of maximum velocity that we want to make our accurate measurement at. And in this case, it introduces 8.76% of inaccuracy. So what does a flow conditioner do? And what does a flow conditioner do in a scenario such as this one? So a simple explanation I would give of a flow conditioner is an element that would be installed in a pipe upstream of an instrument, upstream of a flow meter, to basically knock out some of the disruptions in the flow to create a swirl-free, more uniform flow profile that could help with the accuracy. Now, you won't have that ideal bullet-shaped parabola, but the flow will be uniform. It won't have the swirls, and meters calibrated with the flow conditioner will be capable of making a much more accurate measurement in those less than ideal conditions. So on the top, we see an elbow and we see plenty of straight run. On the bottom, we see an elbow and we see the instrument is installed much closer to the elbow and is still able to make an accurate measurement. So it reduces that required footprint that you would need. So in the same example, the flow plate reduces the uncertainty or the added inaccuracy from 9%, 8.76, down to 1. So going back to this example here, installing an elbow, installing a VIP plate, which is our flow conditioner, would reduce the inaccuracy down from 18% down to 0.8. So it gets you under that 1%. You've got obstructions, you have a smaller footprint, you have a valve. A flow conditioner can really help in a scenario such as that one. So looking at this same scenario here, the convergence, the butterfly valve, the elbow downstream, the flow conditioner, looking at this scenario here, from the standpoint of a pressure loss, we'll talk through what type of pressure loss the instrument adds versus what the flow conditioner adds. So without a flow conditioner, without the VIP plate, our insertion type meter and many of its type, the pressure loss is almost negligible. It's about 0.087 psig at a flow rate of 5,500 SCFM. When you add in the plate and when you add in the VIP plate, it increases to a still very manageable 0.61 psig at 5,500 SCFM. But looking at the overall pressure loss that you would see here, most of it, 87% of it, the total being 0.61, is from the flow conditioner, which raises the question: do some flow conditioners cause more pressure drop than others? And the answer to that question is yes. We have several different types of flow conditioners that we offer. One of the most prevalent is the VIP plate. It's part of our VorTab line of flow conditioning. There are several different technologies that are out there, your tube bundles, your Gallagher plates. And in studies that we've run, some of the different technologies, they do bring about anywhere between 33 and 90% more pressure loss. So flow conditioning can help with inaccuracies. But when you select a technology, it is also important that you be informed and take a look at what type of pressure loss the flow conditioning element will introduce. So overall, wrapping it up here, got all of the animations. There's 2 key points. One, have 20 diameters upstream and 10 downstream so you can make an accurate measurement. If you don't have that for any reason, we would encourage you to work with your suppliers to look into flow conditioning as an option. And point 2, a flow conditioner or really any instrument that you introduce into the process can cause pressure loss. So it's important to also work with your suppliers to understand what type of pressure loss you'd be looking at. So that is my presentation. I'll conclude with that. We do have a couple of leave behinds here. If you visit our website, we have a gas flow measurement application guide. We have basically an ebook on wastewater applications, and we encourage anyone here to follow us on LinkedIn. Thank you.
Great job, Adam. Thank you very much for the presentation. And I'm glad we're leaving up on the screen the website for the company. So again, for any of our attendees, if there's any questions for Adam, please feel free to follow up with him via email. I'm sure he wouldn't mind hearing from you. Again, his email address is on the left-hand side of your screen where the speakers are listed. And also, please feel free to visit FCI at the website that they have here on the screen, as well as on Water Online. So Adam, thank you very much for your time. Great job with the presentation, very informative, and I look forward to having you back.
Thanks, Travis.